Hello and welcome to this Mr. Cole chemistry video going through the energetics practice test. Question 1 is a multiple choice question regarding standard enthalpy change of formation. You have to know the definition of this term. Standard enthalpy of formation is the enthalpy change when 1 mole of a substance is formed from its elements, with all substances being in their standard states in standard conditions. A is false because barium is a gas in the equation given. It should be a solid. B is false because it has ions in the equation. This equation is actually the lattice enthalpy of formation, something that you will come across in the thermodynamics topic. Answer C. Answer C is correct. It's the elements in their standard states forming the product. D is wrong in a whole range of different ways. We've got ions where they shouldn't have them. We've got strange states where we shouldn't have them. So, as we said, the answer is C. 2a wants you to write the equation for the formation of iron 3 oxide. We've already defined the enthalpy of formation as the enthalpy change when 1 mole of a compound is formed from its elements, with everything being in their standard states or standard conditions. So we start off with iron and oxygen, and the iron, which has to be a solid, and the oxygen, which has to be a gas, going to form iron oxide as a solid. We then balance it by putting a 2 here and a 3 here, and therefore need a 4 here. Question 2b is a Hess's law question. I always draw out the Hess diagram, no matter how easy I think this question might be in my head. Start by writing out the equation that you are given in the question. Look to see which data we have. We have formation data, and as we know, formation data is forming compounds from your elements. Therefore, the other 2 arrows in the Hess diagram need to be elements going to compounds. This means we need to have elements along the bottom. Note the direction of the arrows are pointing upwards. It's not always the case, but in this particular case, we're going from the elements to the compounds using the data we've been given, so it has to go from the bottom, which is the elements, to the top, which is the compounds. The next step is to put the data into the Hess diagram. We're given the enthalpy change for the reaction along the top, so we can just write that in. And the arrow on the bottom left is the formation of carbon monoxide and Fe2O3, so we can put those in as well. Not forgetting to take into account the fact that there are 3 carbon monoxide molecules. The arrow on the right is the formation of iron, which is just going to be 0 because iron is an element, and the formation of CO2, which is what we're trying to work out. I like to add in a big curved arrow to show the route that I am taking in my Hess diagram. Note that my big curved arrow starts where my question mark arrow starts and ends where my question mark arrow ends. It just goes via a different point. Any arrow that goes in the same direction as my curved arrow is added, and any arrow that opposes my curved arrow is subtracted. In this case, both of them are just added together, so our equation is this. It would be very easy to stop there thinking you've finished. However, you have worked out the value for the arrow on the right here. The arrow on the right is for 3 times the formation of CO2, therefore we need to divide it by 3 to get the value for the formation of CO2, which gives you an answer of minus 391.3. Note the significant figures in this question. The mark scheme says anything acceptable higher than 2. Looking at the question, you've got 3 sig figs and 2 sig figs given to you in the question, so really the answer should be to 2 sig figs, which means the answer would be minus 390. Question 2c is a bond enthalpy question. Again, I would draw a Hess diagram here. Start with the equation that you're given at the top of the table, and then add the atoms along the bottom like so. Note that the direction of the arrows is different to the last question, as per the equations given to you in the table. As always, you should put the values into the Hess diagram and draw the big curved arrow. Like in the previous question, just make sure that you have multiplied any numbers that you need to. So for example, the hydrogen has to be multiplied by 3. So any arrows that oppose are subtracted, and any arrows that go in the same direction are added. Therefore, the equation is this. As before, don't forget that this is not the final step. What we have worked out here is the arrow on the right. What we're trying to work out is the bond enthalpy for the NH bond. There are 6 NH bonds in that arrow on the right, because there's 3 in each ammonia molecule and there's 2 ammonia molecules. Therefore, we have to divide this number by 6 in order to get the final answer. And again, like the previous question, we have a question of the significant figures. The mark scheme accepts 2 or more significant figures. You should give your answer to 2 or 3 significant figures, and really 2 is the correct answer. So the answer is plus 390, not plus 390.7, like everything there. So question 2D wants you to explain why the value you've just calculated there is different from the mean bond enthalpy quoted in the data book. Now, the thing that's important to note is that the environment that a bond is in affects its bond strength. So the nitrogen-hydrogen bond in ammonia is going to be different to the nitrogen-hydrogen bond in, say, an amine, such as this. The presence of the carbon there will impact the strength of the bonds. Therefore, when you have a mean value in a data book, it is the mean value across a whole range of different compounds, not just the NH3 molecule. Your answer is worked out just looking at the NH3 molecule. Question 3a is a definition. You just have to know this. Enthalpy change is the heat energy change at a constant pressure. Question 3b is another definition that you just have to know. Hess's law states that the enthalpy change of a reaction is independent of the route or path taken. Question 3c is another Hess diagram. They've been nice enough to draw it in, so let's put the data into it. Put in the curved arrow to see which direction you're going in, and add everything that is going with the arrow and subtract everything that is going against the arrow, which gives us... Okay, so question 4 is a calorimetry question. There's a couple of different steps involved in a calorimetry question. The first thing that you have to do is use MC delta T to work out the energy change of the reaction. In order to do that, though, we have to use the graph in order to work out the temperature changes. Now, this sort of temperature change graph is useful because it allows you to work out what the temperature change would be despite the fact that there was heat loss occurring in the reaction. What you have to do is you have to determine the temperature at which the reaction started and determine the temperature at which the reaction would have been if there had been no heat loss, which is to say what the reaction would have been, what the temperature would have been if the reaction had taken 0 time at all. So we need to use the graph to extrapolate to the time at which the mixture occurred. So here are my 2 extrapolated lines, both extrapolated back to 4 minutes, which is the point where the mixing occurred. You can see that the lower line, the left-hand line, extrapolates along to 23 degrees C at 4 minutes, and the upper line extrapolates to 40 degrees C at 4 minutes. This means that the temperature change, if there were no heat loss, would have been 17 degrees C. Okay, so now that we know the delta T, which is 17, we can work out Q. So Q equals mc delta T. M is the mass of the thing that you are heating up, C is the specific heat capacity of that thing, and then delta T is the temperature change that we've just worked out. In all of these examples, what you will find is that you're either mixing 2 solutions or you're putting a solid into a solution. The mass that we use is the mass of the solution. This, of course, isn't really strictly speaking true. This is an approximation. However, it's a very good approximation, and we're using the specific heat capacity of water in this. So C is the specific heat capacity of water. And actually what we're saying really is we're heating up the water that our substance is dissolved in. It's not 100% accurate, but it's close enough to the truth that it gives you a pretty good answer. So Q equals mc delta T. The mass then is the mass of the solution, which is the mass of the aqueous trichloroethanoic acid. We can assume that the density of this is 1, because all of the solutions that we deal with have a density of 1, and therefore the mass of the aqueous trichloroethanoic acid is 10 grams. So Q equals mc delta T is 10 times 4.18 times our temperature change of 17, which gives us 710.6 joules. The next step is to convert Q into delta H. Delta H is equal to Q converted into kilojoules divided by the number of moles. The moles of what, of course, depends on the reaction we're looking at. It is always the substance that is limiting. We're told in the question that the trichloroethanoic acid is in excess, and therefore the limiting substance is the magnesium. So delta H is equal to Q converted to kilojoules divided by the number of moles of magnesium. So the next step then is, let's work out the number of moles of magnesium. So we've got the mass of 240 milligrams, which of course is 0.24 grams, divided by the MR, or the AR, which is 24.3, which gives you 0.00988 moles of magnesium. The final step then is to work out the delta H from the Q. Delta H is equal to minus Q divided by 1,000, so that's converting our Q into kilojoules, divided by the number of moles. Now we do have to be careful about significant figures here. We are told in the question that we have to give it to an appropriate precision. In a question like this, you need to look through the data you've been given and determine what the number of significant figures is. Now, it initially looks like 3 significant figures in most cases. 3 significant figures, 3 significant figures, 3 significant figures. But you have to pay attention to the graph. The graph has been given, temperature-wise, to 2 significant figures. Now, times actually to 1 significant figure, but you're not actually measuring time, so it doesn't matter. You can ignore that one. So 2 significant figures is the minimum number of significant figures used in the data, and therefore you should use 2 significant figures. So the answer is 72 kilojoules per mole, not 71.9, which I think quite a lot of people will be tempted to give as their answer. Question 5a is another definition question. Now, when it comes to defining terms like this one, you don't have to be defining the enthalpy part of the description, it's just the of combustion part. So you can start by saying it is the enthalpy change when. Now, be careful with this. Lots of people want to talk about energy, and I wouldn't. I'd talk about enthalpy. And people want to talk about energy giving out or taken in, stuff like that. You don't need to try and explain whether it's giving out energy or taking it in. In something like this, it's kind of obvious it is giving it out, but in other cases, it's not going to be obvious whether it's taking it in or giving it out. So don't try to explain it. Using the phrase enthalpy change when is always going to be correct. So we'll start with enthalpy change when. Then the next part of a definition is always to talk about the number of moles of a substance being changed or affected. Okay, we of course are always going to be talking about 1 mole. So enthalpy change when 1 mole of a substance. The second part of the definition then is to be looking at what is actually happening. So it's burned in oxygen or reacted with oxygen. But you have to make it clear that it is complete combustion or with excess oxygen. Okay, so there are actually 2 different types of combustion. There's complete and incomplete. And enthalpy change of combustion is actually really the enthalpy change of complete combustion. But we don't say the word complete in the name. So far we've got enthalpy change when 1 mole of a substance is completely burned in oxygen or reacted with excess oxygen. The final part of any of these sorts of definitions is talking about the states involved. There's 2 different scenarios. The first is that your states are standard conditions, standard states and standard conditions, or the second option is as gases. In this particular case, we're talking about the standard states and standard conditions. So you want to either state those standard conditions or you want to just say under standard conditions. So enthalpy change when 1 mole of a substance is completely burned in oxygen under standard conditions. Standard conditions. So the next question is another calorimetry question. So like before, we'll start with Q equals mc delta T, although unlike before, we don't need to use a graph to work out what the enthalpy change is, or don't need to use a graph to work out what the temperature change is. So Q equals mc delta T. So looking at our equation there, M is mass, and it's the mass of the thing being heated. So it's 150 grams of water, not 2.12 grams of methanol. And 4.18 is, of course, the specific heat capacity of water, times by the temperature change, which is given there in the equation. If you're struggling to remember which mass is the mass that goes into the equation, just remember the mass and the specific heat capacity are for each other. So if you're looking at the specific heat capacity of water, then it's the mass of the water. If we're going to work out delta H, we need to use the equation delta H equals minus Q divided by 1,000 over the number of moles. Therefore, we need to know the number of moles. Because this is enthalpy of combustion, there's no question about which moles we're going to be using. It's going to be the moles of the fuel. Moles equals mass over MR, so mass of 2.12 divided by the MR of 32 gives us 0.0663 moles of methanol. And now we know the number of moles and we know the energy change. We can work out delta H by using minus Q divided by 1,000 over the number of moles, which gives us 605.249 kilojoules per mole. It doesn't tell us in the question that there's a particular number of significant figures that it wants us to use, so we just need to apply our common sense and use an appropriate answer. Take a look at what's being used in our question. We've got 3 sig figs for the mass, we've got 3 sig figs for the mass of water, 3 sig figs for the temperature, and 3 sig figs for the specific heat capacity. So I think 3 sig figs should be our answer. So 605.249 is 605 kilojoules per mole. Okay, so this is another Hess diagram question. So let's start by drawing a Hess diagram. As always, start by writing the equation that you're trying to figure out at the top. Now the next bit, which is relatively difficult, is figuring out what you're going to be putting along the bottom down here. Now you've been told to use stage 2, and you've been told to use the combustion of carbon monoxide and hydrogen. Now combustion data is obviously always going to be producing the oxide and water. In the case of carbon monoxide, it's going to be making carbon dioxide, and in the case of hydrogen, it's going to be making water. So what we're going to want to have is we're going to want to have CO, and we're going to want to have hydrogen along the bottom here. That's going to then result in our arrow here being our combustion of CO and our combustion of hydrogen. We do, of course, need to make sure this balances. So if you look on the top right, we've got 2 lots of H2O, which means we've got 4 hydrogen atoms, which means we're going to have 4 hydrogen atoms on the bottom. So we're going to have 2 lots of hydrogen there. Then the next question then, of course, is what's the arrow on the left going to be? Well, we've been told to use stage 2. Stage 2 is the reaction between carbon monoxide and hydrogen producing methanol. Well, that's exactly what's happening in the arrow there. So that's our stage 2. There is, of course, one thing missing, which is the oxygen on the bottom. The bottom there, of course, are the enthalpy change for combustion. So we do, in fact, want our oxygen on the bottom, which is going to be 1.5 oxygens, which balances out our number of oxygens on the top right and on the top left. Okay, let's put some numbers in and then we'll do our calculation. So starting with stage 2 on the left, and then on the right we have our enthalpy change of combustion of carbon monoxide and the enthalpy change of combustion of hydrogen, which of course there is 2 of. on their right hand side. The next step then is to add our big curly arrow into it. So we're starting off over on the left, we're ending up on the right, but we're going via the bottom. So we're going to look like this. Then we need to do our calculation, and remember, of course, anything that goes with the arrow is added, anything that is against the arrow is subtracted, which gives you minus 764. Question 6a is to write an equation for the complete combustion of propanone. So we'll start by writing in our reactants and our products. Now that we've got our right substances, we need to make sure we've balanced them. The starting point is by looking at the number of carbons. So we've got 3 carbons on the left, and therefore we need to have 3 carbons on the right. And the second place to look then is the hydrogens. We've got 6 hydrogens on the left, and therefore we need to have 6 hydrogens on the right. That means we need to have 3 waters. Now that we've balanced the number of carbons and hydrogens, the last thing is to balance the number of oxygens. And you will see that we have 9 oxygens on the right hand side. We therefore need 9 oxygens on the left hand side, but it is important to remember there is an oxygen in the propanone. So actually we need to have 8 oxygens as part of the O2s, and therefore we need to have 4 O2s. Question 6b1 is asking us to calculate the number of moles of propanone in 1.45 grams. Moles is equal to mass over MR, and therefore we need to start by working out the MR of propanone. 3 lots of 12, 1 lot of oxygen, so 1 lot of 16, and 6 lot of hydrogen, so 6 lots of 1, gives us an MR of 58. Therefore, the moles is equal to 1.45 over 58. Which gives us 0.025 moles. Question part 2 is just Q equals mc delta T. So we've got the M of 100, which is our mass of water, times by 4.18, times by the temperature change, which is 351.2 minus 293.1, which gives you 24,300 joules. Part 3 then is to work out the value in kilojoules per mole for the enthalpy of combustion of propane. So we've worked out Q and we've worked out the moles, so delta H is equal to minus Q divided by 1000, that's converting our joules into kilojoules, over the number of moles. So that is 24.3, so that's my 24,300 divided by 1000, divided by the moles of 0.025, which gives us an answer of minus 972. Minus 972 kilojoules per mole. They haven't asked for the particular number of sig figs, so use what's in the question, use the minimum what's in the question. The minimum is 3 sig figs. Question 6c1 appears to be a similar question to 2d. However, they are different to each other because 2t is about bond enthalpies, whereas this question is about enthalpy of combustion. The values are different because the experiments were done differently, or alternatively, one was more accurate than the other. The reason for this is that the experiment completed has some energy loss as heat to the surroundings. So you can see my answer there of heat loss. You cannot give incomplete combustion as an answer in these types of question because you are told in the question that the propanone was burned completely. Okay, question 6c2. The easiest way to get your head around this question is to draw a Hess diagram. Now, I wouldn't actually recommend that you draw a Hess diagram to answer this question, but if you're struggling to understand why the answer is what it is according to the mark scheme, a Hess diagram will help you get there. So if you draw out the Hess diagram for this reaction with a gas, and then a separate Hess diagram using it as a liquid, you can see the difference. So you can see on the left-hand side, we have the Hess diagram, which we would get if we were using liquid water. Now this is the normal Hess diagram, because water under its standard conditions and standard states is going to be a liquid. The one on the right is what we actually have in the reaction, which is producing water as a gas. Now you can see that the difference between these two is that there's an extra step. the one on the right hand side, if you want to go from C4H8O, you want to combust it and you want to result in liquid water, yes, you have to do that same reaction, that steps which I've labelled as C, but then you also have to do step D as well. What it means is we need to know what step D is. Well, step D, you can see that nothing is happening to the carbon dioxide, but you can see that the water is turning from a gas to a liquid. So in order to know what the overall effect of C and D is, we have to know whether turning water from a gas to a liquid is an endothermic reaction or an exothermic reaction. So you have to think about this in terms of the movement of the particles and the energy of the particles. When you go from a gas to a liquid, the particles themselves are going from moving around a lot to not moving around very much at all. This means that they had to give out energy in this process. The energy had to go somewhere else. It was previously in the water molecules, and now it's left the water molecules. Therefore, D, going from gas water to liquid water, is an endothermic process, a little counterintuitively to some people. This means D has a negative value. So overall, going from butanone to the products of combustion as a liquid is going to be a slightly more negative value than going to the products of combustion with water as a gas. Therefore, the answer is more negative, because energy is released when water is condensed. Question 60 is another Hess diagram question. This one is based on combustion data, so as usual, start by writing the equation that you're trying to calculate enthalpy for along the top. Then, as it is combustion data, place the oxides along the bottom. Note the direction of the arrows. Of course, this is combustion data, so the arrows are pointing in the direction of forming the oxides. Next, we add in the values and draw in the big curved arrow to show the route that is being taken. As usual, any arrow that is going the same direction as our big curved arrow is being added, and anything that is opposing it is going to be subtracted. So our calculation is this. 3 sig figs are used in our answer because the majority of the information is to 3 sig figs in the question. Question 7 is a multiple choice question. It is, however, just a Hess diagram question. Even though it's a multiple choice question, I would still recommend drawing out your Hess diagram. Note that all the values in the table are bond enthalpies, so it is the energy that is required to break the bonds, so the arrows are pointing towards the individual atoms. So we are trying to work out the bond enthalpy of the C triple bond O, which means that we are trying to work out the bond enthalpy of the one on the right. So we're trying to work out this arrow here, which means that we are trying to work out that arrow there, which means we need to know the top arrow and the bottom left arrow. So the top arrow we given in the question is plus 206. So plus 206. And the left arrow are the 4 CH bonds in the methane, so 4 times 413, and the 2 OH bonds in the water, so that's 2 times 463. So in order to work out that arrow on the left, it is minus plus 206 plus 4 lots of 413 plus 2 lots of 463, which gets us 2372. Now, of course, we haven't got the answer here. What we have is the value for the right-hand arrow. The right-hand arrow is made up of 2 things, the C triple bond O and the 3 HH bonds. So once we take away the 3 H bonds from our value of 2372, that gives us the value for the C triple bond O. That gives us 1064, so our answer is B. Question 8 is a slightly strange question. It wants you to state the change in volume that would cause a reduction in the heat loss. But in order to do that, we have to think about why heat loss occurs. Heat loss happens when there is a difference in temperature between 2 different areas. So in this case, if the area, which is the water, if the water is significantly hotter than the surrounding areas, then heat will move from the water to those surrounding areas. The larger the difference in these two temperatures, the larger the amount of heat loss is going to be. So what we want to be able to do then is minimize the temperature increase. Well, how can we minimize the temperature increase by only changing the volume of water? Well, the larger the volume of water, the lower the heat loss will be, because the larger the volume of water, the lower the temperature rise will be for the same amount of energy transferred. So our answer is increase the volume, and therefore there will be a smaller increase in temperature. Smaller increase in temperature above room temperature. Question 9 is another Hess diagram question. So let's start by drawing out our Hess diagram. And as you can see from the Hess diagram and the calculation below, the answer is minus 42. Okay, so that brings us to the end of this walkthrough for the energetics practice test. If you have any further questions about any of those questions, please leave a comment. And if you like the video, please leave a like.